Thanks everyone for coming. I think we have less people today because most people are out on spring break. Good job to those of you who are actually here because the math grind never stops. Am I right? Today we're going to be doing modular arithmetic. I know I said a couple of weeks back that I was going to do this. Last class was more chill than usual, I would say. This time we're going to really go in depth. And this is kind of a tricky topic, but like if you want to do competition math, you have to learn this, right? Um, Basically, there are like four different like disciplines in like competition math. It's like algebra, number theory, geometry, and counting and probability. Basically, every single number theory question is based off of modular arithmetic up until like Olympiad level, right? You probably will have to learn this at some point. So I thought it'd be a good idea to do it now. So basically, first we have to discuss what modular arithmetic is. So when we divide two numbers, right? Let's say A and B, we get a quotient Q and a remainder of R, right? So for example, if we divide 16 by 3, we get 5, and then our remainder is 1, right? So we always get a quotient and a remainder, right? And when they're doing number theory, we don't like having fractions, right? Because number theory is a study of the integers and like Diophantine equations, right? So we don't really like fractions. We don't really like decimals at all when we're doing number theory questions. So what are we going to do then? Basically, we come up with a system called modular arithmetic, right? So modular arithmetic only concerns itself with the remainder, right? It doesn't tell us anything about this. We don't care about what the quotient is, right? When they're dividing. So we say that we express sort of this idea with the remainder of 1, sort of like this. So if A over B is Q with remainder R, we get A is congruent to R mod B, right? So let's break down this, what this equation means, right? So in this equation, for example, we have 16 is congruent to 1 mod 3, right? Notice that the 5 is not in here because we don't care about how many times the 3 goes into it, just the remainder. So what this equation is saying is 16 has a remainder of 1 when you divide by 3, right? In this general form, A has a remainder of R when you're dividing by B, right? Sort of like this. And then, for example, 37 over 4 has a remainder of 1. So we say 37 is congruent to 1 mod 4, right? And for example, if I asked you, I was like, can you calculate for me what is like 17 mod 5? You would go, okay, I divide 17 by 5 and I get a remainder of 2, right? So 17 is congruent to 2 mod 5 because it has a remainder of 2 when we were dividing by 5. Okay? Does this make sense? I'm going a little bit more slowly here because it's a very, very new concept and it gets much harder later. Just tell me if you don't understand anything that's going on, because then you'll probably be very confused for the rest of the lesson. No questions? Okay. So what if I asked you, what is 19 mod 6? Can anyone tell me what 19 mod 6 is?
1.
Yeah, it's going to be 1, right? 19 is congruent to 1 mod 6. Right? Because 18 is a multiple of 6, 19 is one more than that. Okay, nice. So now we're going to introduce something called a congruence, right? Um, in some of the resources that you'll read and that you'll see here, we sometimes write it like this, which is how we write like congruences in geometry because it's sort of called the same thing. I like to write it like this with 3 lines because I don't drawing this squiggle is kind of complicated. You can do whatever you want though. So basically, a congruence basically means these two things are equal when you're only considering the remainders, right? So for example, 52 is congruent to 27, is congruent to 24 mod 7. right? What does this mean? 52 and 24 are the same if you're considering only the remainders. They have the same remainder when you're dividing by 7, right? So both of these are congruent to 3. So you can sort of write it like this, right? 52 is congruent to 3 mod 7, and 3 mod 7 is also congruent to 24 mod 7, right? Because 24 is 3 mod 7, 52 is 3 mod 7. So 52 is congruent to 24 mod 7, right? And this is like a very basic congruence. Remember on the last slide, new person. Okay. So do you guys remember on the last slide when I was talking about how what was the question that came up? It was like, oh, 19 mod 6, right? I was like, what is 19 mod 6? Well, there's actually an infinite number of ways you can answer this question because 19 is congruent to, first of all, 19 is congruent to 1, is congruent to 7. All of these have the same remainder mod 6, right? So that question is kind of misleading, but generally when we ask this, we're talking about the number between 0 and 5 for mod 6. Okay, so with this in mind, we don't have to worry about this for now, but what we have to realize is if something is congruent to 0 mod a number, it's divisible, right? So if I say A is congruent to 0 mod 3, what we know is that A leaves a remainder of 0 when we're dividing by 3. What that means is that A is basically just a multiple of 3, right? If A leaves a remainder of 0 when it's divided by 3, A is a multiple of 3. Okay, that's pretty easy. So where this begins to get very useful is we can sort of make equations using variables with these modular arithmetic properties, right? So for example, if we know that A plus B equals C, so this know that this is equals, which means they're actually the same number, then we can actually just take the whole equation mod any number n that we want. So we can have A plus B equals C. We can turn this into A plus B is congruent to C mod n. And if you think about it, this makes sense, right? Because if A plus B, and C are the same number, then they definitely have the same remainder when we're dividing by whatever number we want, right? So in a way, this is less specific than our original equality. But we can do a lot more cool things with this than we probably could have with this, and we'll see this a little bit later. Because you can do many cool things and simplifications here that you would not be able to do with this. Okay. Our next thing is that basically anything that you can do to an equality, you can also do to a congruence. Because a congruence is less specific than an equality. So, for example, here you can add the same number to both sides. So, for example, other example, 7 is congruent to 1 mod 3. They have the same remainder when we're dividing by 3, right? If we added 1 to both sides, we would get 8 is congruent to 2 mod 3, which is definitely still true. We can add whatever number we want to both sides. Moreover, this property, I forget what it's called. It's not transitive property. Whatever. So, but this property still holds, right? So if A is congruent to B and C is congruent to D, then you can just add the two like congruences together. To get A plus C is congruent to B plus D mod n, right? So we can also add these congruences together. Finally, if A is congruent to B, then negative A is congruent to negative B, because you can just take the same thing on both sides. But this raises a question. Do negative remainders make sense? Well, we actually define negative remainders like so. So for example, let's say we want to find -1 mod 3, right? A lot of questions use this -1 property. So it is very important that we define negative numbers here as well. So what we know is that 3 is congruent to 0, right? Right, because 3 is just a multiple of 3. So what we can do is we can just add 3 to this, and it'll still be the same number mod 3, right? So 3 plus -1 gives us 2. So this is actually congruent to 2 mod 3, right? So -1 is congruent to 2 mod 3. Huh? So for example, if I wanted to ask you about -2 mod 7, you could say, okay, -2 mod 7 is simply 5 mod 7. Mhm. All right. So hopefully all of this made sense. You can send me a message in the chat if you didn't understand any of that. But for now, this is just some very basic stuff that we're like sort of ironing out. Okay. So let's look at an example of where modular arithmetic, this sort of basic modular arithmetic, we can use to think about a problem in real life. So with this question, it's currently 7 p.m. What time will it be in 1,000 hours? Right. So you guys don't have to use modular arithmetic to solve this first problem, because I'll sort of explain how to use modular arithmetic for this problem, because it's kind of hard to see if you haven't used it before. Yeah, so just send me your answers in the chat when you guys are done. Yes, Charlie, that is correct. Good job. Okay. So we have a lot to get through. So I'll give you guys like a minute or so, and then I'm gonna start explaining. So, for this question, um, we are given that it's currently 7, and we want the time in 1,000 hours, right? So how do we calculate this time in 1,000 hours? Well, um, we know that every 24 hours we get back to the same time, right? After 24 hours, we're back at 7 o'clock p.m. After another 24 hours, we're back at 7 p.m., right? So we can just be like, okay, after 1,000 hours, it's the same as after 1,000 minus 24, right? Which is the same as 1,000 minus 24 times 2. And we keep on going down. And what we're eventually doing is finding the remainder when we divide 1,000 by 24, right? So let's just divide 1,000 by 24 real quick. I think this is 4. It gives us 96. Hopefully this is correct. um, Yeah, okay, that's good. So here we have 40, and then this goes in one more time to give us this, and then 16. Okay, so it's 41 remainder of 16, right? So what this tells us is in 1,000 hours, 41 days will have passed, right? And after 41 days, we're still at 7 p.m. And then we just need to add on an additional 16 hours, right? So we can go forward 5 hours to get to 12 a.m., right? And then we need to go forward 11 more hours to get to 11 a.m. Right? So this is the first way you can do to get your answer. And this is like the generic way that if you've done math counts before, if you're in middle school, you've probably seen at least something like this before, right? So usually it's in like days of the week or years or something, but there's usually something like this. Okay. So the second way that we can do this problem is using modular arithmetic, right? And here's what this looks like. So first, we express every single hour mod 24, right? Why mod 24? Because 24, we just want the remainder when this is divided by 24, right? Like this so. So every 24 hours, like for the purposes of our problem, nothing happens, right? So that's perfect for a what's it called? Modular equation. Modular whatever, right? So first we have 1000 mod what's it called? 24, right? So this added on to 7 o'clock p.m. should give us our answer, and it's indeed the same as up here. What we can do further with this is we can say 17 o'clock p.m. We can just put this on like a 24-hour scale because that's probably easier to think about than a.m. and p.m., right? So 17 is basically 19 o'clock, right? So basically what we're doing is we're doing 1000 mod 24 plus 19 o'clock, right? And essentially what this is 1019 mod 24. So this is actually the answer that we're looking for. Since this is congruent to 11 mod 24, then our answer is just 11 o'clock a.m., right? Um, yeah, I have to admit this is not the best example to do this problem, but you can sort of see where I'm getting at, right? So every 24 hours, nothing happens. So 24 hours equals 0. So we don't care about every 24 hours that passes. Okay. So similarly, we can sort of look at these questions the same way. So for example, on a 12-hour clock, what time is it when it is 12 hours after 11, right? So here we don't care about AM and PM, so we can take this mod 12, right? So 52 hours after 11 is 52 plus 11 mod 12, right? Which is congruent to 3 mod 12. So it'll be 3 o'clock. Right? So again, don't worry too much if you didn't understand this. This is not the main use. You can still do this a normal way if you really wanted to. And this is just like a cool exercise if you wanted to sort of do that as well. Okay. Now we're going to move on and try and use what we've learned and sort of manipulate equations in certain mods, right? So here we want to calculate 31 plus 148 mod 24. Right? So what is this asking? It's asking, what is this when we're dividing, what is the remainder when they're dividing this by 24, right? And how do we solve this problem? So first, what we can do is we can add these two up to get like 179 and then divide by 24. But I don't want to do that because this looks very hard and complicated to do. So instead, what I'm going to do is I can actually evaluate these separately, mod 24, right? So since 31 is congruent to 7 mod 24, and 148 is congruent to 100, right? I can make that a little bit clearer as to why. It's congruent to 100 plus 48. It's congruent to 100. Is congruent to 96 plus 4 is congruent to 4 mod 24, right? Make sure you see like why every step in here is the same mod 24. When we want to calculate their sum, mod 24, all we need to do is calculate their remainders and add them up. So this is congruent to 7 plus 4 is congruent to 11 mod 24. So our answer is 11. Does this make sense to everyone? Yeah. So the real trick with modular equivalences and like modular arithmetic is you can replace any number inside with a number that's the same as it in that mod, right? So it doesn't matter if we were talking about like one, it doesn't matter if we're talking about like 148 to the power of 31 mod 24 or something like that. We automatically know that we can substitute this 148 into as 4. So this is congruent to 4 to the power of 31. We can't do the same thing. We can't do the same thing with 31, unfortunately, but we can do this with the base of our exponent. So this is really the key point of modular arithmetic, is you can replace any number, like logically any number, with its equivalent representation. Uh, So this is sort of more of the same thing. So why don't you guys try this question and send me your answers in the chat? Yeah, Charlie, that's correct. Good job. Oh, yeah, Dylan, that's correct. So the big trick here and the thing I'm trying to get you guys to get used to is substituting numbers before you evaluate them in certain mods. Because sometimes the values that you'll be given in mods of arithmetic are simply way too big for you to simply just like to try and evaluate the whole thing and then divide by whatever number, like arithmetic style, right? So here we want the remainder when this is divided by 3, right? In other words, we want this mod 3. Right, we want this expression mod 3. What can we do? We can substitute every single number in here with its equivalence mod 3, right? So 123 is divisible by 3, so it's congruent to 0. 234 is also congruent to 0. 32 is congruent to 2. 56 is congruent to 2. 22 is congruent to 1. 12 is congruent to 0, and 70 is congruent to 0. So this is actually just congruent to 5 mod 3, which is congruent to 2 mod 3. Right, so its remainder is 2 when they're dividing by 3. Right, so this is how you do these questions very fast. And as you come across more difficult questions, this also works. Right. So I'm not sure if we'll see it later on today, but I will be explaining, if we have time, some of the divisibility tricks or whatever that we learned a couple classes ago using modular arithmetic. So you guys will get to see it in action then. Okay. So next we're going to talk about multiplication because we already talked about addition, and I feel like a lot of you guys have a good grasp on addition already, right? So for multiplication, it works basically the same way, right? So as like addition in relation to like equation or like the equal sign, right? So here a times b equals c, then we can take the entire equation mod n. So ab equals c, a times b. So then a times b is also congruent to c mod n, right? You can multiply the same thing, it doesn't matter. Um, and also something like this. The one thing you have to be careful of when you're multiplying by k is you have to make sure that k and n are relatively prime, right? Because think about it. If k is congruent to 0, you're just you're multiplying by 0 on both sides, which you can't do, right? So, yeah, just keep that in mind. A k has to be like relatively prime to n. Okay. And then here the same thing. So if A is congruent to B, C congruent to D, then AC congruent to BD, right? So here is this example. What is 8 times 16 mod 7? This is probably the clearest and most simplest example you can get of the efficiency of modular arithmetic. So why don't you guys like, it shouldn't take you guys that long to do. So I'll give you guys like 2 minutes or so. Yes, Charlie, that's correct. So, what I bet that those of you who got it or are solving it right now are doing is you're taking 8 times 16, right? From which you would have gotten 128, right? And you divided it by 7, and then you got 18 remainder 2, right? And then you're like, okay, remainder is 2, easy, right? But the cooler way to do this, and the much simpler way, is you can replace each number here with its equivalent mod 7, right? So what this looks like is this. So 8 mod 7, 8 is congruent to 1 mod 7, right? 16 is congruent to 2 mod 7. So we can replace 8 with 1 and replace 16 with 2. So what this is asking us is what is 1 times 2 mod 7? So the answer is just 2. Isn't that cool? So the reason why this works is something like this, right? So we know that 8 is 1 mod 7. So what this tells us is 8 times 16, we just really split it up into 7 plus 1, and then 2 times 7 plus 1, right? And then if you try and FOIL this out, expand this out, you get 7 times 2 times 7 plus 2 times 7 plus 7 plus 1, right? Which is 1 times 1 over here. Or it should be a 2 times 2, right? Something like this. And you notice every single other term here has a 7 except for their remainders multiplied together, right? And since 7 is functionally equivalent to 0 when they're talking about mod 7, we can just pretend these don't exist. We're only worrying about the remainder, which is just 1 times 2, which is 2, right? So whenever we're doing something like this, we can replace them with their equivalents, mod, whatever number here, right? So I'll just give you guys another example. So what is 9 times 10 mod 4? Nice, yeah. So what we do here is we say 9 is leaves a remainder of 1 when you're dividing by 4. So you replace a 9 with a 1, and then you replace the 10 with a 2, because 10 is 2 mod 4. So then you get congruent to 2 mod 4. Right? Isn't that so much easier than multiplying and then dividing by 4? Or it actually works. The reason why this is so useful is when you get to bigger numbers, it's very helpful. So for example, let's say you wanted to calculate 17 times like 20 mod 16, right? You don't want to multiply these together and then divide by 16, right? Instead, what you can do is you can replace the 17 with a 1 and the 20 with a 4. So then you get 4 mod 16, right? Something like this, multiplication. Because multiplication is just repeated addition. So you replace, it's like 17 20s, which is the same thing as adding 17 fours, because 20 is the same thing as 4 when you're talking about remainders for 16, if that helps your understanding. So now I have a much longer problem that you actually can't do just multiplying them all across. So why don't you guys try this and send me your answers in the chat. Yes, Charlie, that's correct. Good job. Your answer should be a number from 0 to 2 because we're talking about remainders. Right. So your answer might be congruent to the remainder mod 3, but you still have to simplify it, right? So make sure you're doing that as well. So for this problem, it's sort of like the same as the last problem, right? So we're going to find each of these things when we're taking them mod 3 and evaluate them and then multiply them together, right? Only after we've done that. Because multiplying all these numbers together and then dividing by 3 is takes a very long time, right? So first, 124, 1 plus 2 plus 4 is congruent to 1. So this is 1. This gives us 1 plus 3 plus 4 is 8, which gives us 2. mod 3. This gives us 2. This gives us a 1. This gives us a 1. And this gives us a 1. Okay. So in effect, this is congruent to 1 times 2 times 2 times 1 times 1 times 1 mod 3, right? And this then is congruent to 4 mod 3. And remember, your answer should be between 1, 0, and 2. We just put this into mod 3, and you have to remember to take it out of mod 3. So this has the same remainder when divided by 3 as 4 does, and 4 has a remainder of 1 when divided by 3. So the answer is 1. Right. So here again, it's like the same thing. Whenever we're doing something like this, you can always just swap it out, right? And you have to understand the concepts here because they're very important when you're doing other things, such as multiplying and adding, right? So for example, let's just use the first 3 over here. If I wanted to calculate 124 times 134 plus 23, mod 3, I would do the same thing, right? 124 is 1. Each of these is 2. So 2 plus 2, which gives me 4, which is going to 1. Right? Nice. Okay. So now we are going to look at exponentiation. So this is by far the most common and most useful use of modular arithmetic that you'll see up until starting from like AMCs up until like Amy. Um, it does come up a lot in not a lot. It doesn't come up that often in the Olympiads, uh, comparatively because there are a lot of these on AMC and Amy, but it does still come up on the Olympiads as well. So basically, for exponentiation, we just note that we can raise these to whatever power we want, right? Because A congruent to B mod n, we can just multiply this by the same congruence as many times as we want. So for example, if we do this once, we get a squared congruent to b squared mod n, right? And we can do this as many times as we want, which is why this exponentiation thing works, right? So here, this generally holds. And what's nice about this is we can actually take this out of our exponent, right? So what this means is that a to the k, right, is congruent to a times a times a times a times a, right? And there's ka's here, right? Which is congruent to, let's say a is congruent to b mod n, right? Which is going to b times b times b, and there's kb's here, right? And then what we can do is we can just take this back to b to the k, right? So a to the k, if a congruent to b, then a to the k congruent to b to the k. So what we can do is we can swap out the base with something that's a lot easier to calculate, right? So honestly, actually, I'll leave this one to you guys to figure out. So I'll give you guys like a couple minutes or so to do this question and send me your answers in the chat. And then I'll go over 2 different ways you could have solved this question. Yes, Charlie, that's correct. Good job. So, when they're doing these types of questions, with large exponents, you have to ask yourself, what are the easiest exponents for me to raise to very high powers, right? Obviously, zero is one. If I can get a zero, that's great, right? Zero to the power of anything is zero, other than zero to the power of zero, but we don't have to worry about that for these questions. So zero is easy, one is easy, right? Because one to the power of anything is one. And one other number that people often forget about is negative one, right? Negative one is also very easy. So it just matters on what the parity of this number is, right? So negative one to the four is even. Four is even, so this relates to one. If it was like three or an odd number, it would value it to negative one, right? So negative one is also a very easy number to take to high powers, right? So when we're doing questions like this, what we really want is we want to get zero, one, or negative one, right? All the time, right? So in here, conveniently, we can actually do this pretty easily, right? So one thing, I guess the most complicated, like not most complicated, the fastest way, but also the most confusing way, the most complicated way, is to realize that 3 is congruent to negative 1 mod 4, right? This comes up a lot in competition math, where it's like thinking outside the box is what they're trying, I guess, to test you for. So you have to actually go to negative exponents to solve it like this, right? So since 3 is congruent to negative 1, remember we said that 4 is 0. So we can just subtract by 4 on this to get negative 1. Or from negative 1, we can add 4 to get 3. So this linear congruence is true. So we know that 3 is congruent to negative 1, so we can substitute it into here, right? So 3 to the 16th is congruent to negative 1 to the 16th, which we all know is congruent to 1, well, 4, right? So this is the first way that you could sort of do this question. The second way that you can do this question is you can notice that 3 to the 16th is congruent to 3 squared to the 8th, right? Or congruent to 9 to the 8th, right? And we know 9 is congruent to 1 mod 4. So we can substitute 9 in for 1. 1 in for 9, that is, right? So it's 1 to the 8th, which gives us 1 mod 4, right? So like this, like so, there are two different ways. The key point here is you want to get zeros, ones, and negative ones when you're doing questions like this, because they're like the easiest that you can manipulate. Okay. So these questions are, I would say, not the greatest. I want you guys to try doing the third one. So just try doing this one for now. You guys can take a look at these two if you want, but yeah. They require something more advanced that we probably won't get to today. Yes, Charlie, that's correct. Good job. Okay. So for this question, um, whenever we're doing questions like this, I guess the very first thing that I like trying is calculating the first few powers of two and seeing if we can get like the -1, 0, or 1 that we talked about before. Because getting one of these inside of one of these basically melts our entire problem, right? So here we have 2 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So 2 to the 1 is 2. We can get to 2 mod 7, not very exciting. Again, not too exciting. Uh, This congruent to 8. Is congruent to 1 massa. Yeah, right. Okay. So, actually, when I was doing this question in my head, like 2 seconds ago, I thought this was -1. So, I guess I made a silly there as well. But basically, now that you see, once I've written it out, it's actually what, right? So 2 cubed is actually going to be congruent to 1 mod 7. And we can really use this fact, right? Because let's check 2 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, right? This top part is divisible by 3, right? Um, the way you can see this is you can add up all the digits like we talked about before in like 2 classes ago or something with divisibility tricks. And we know that this is divisible by 3. So we're going to use this list. Well, we can say this is 2 to the third to the power of whatever this divided by 3 is. We know it's an integer though. So let's call it like n or something like that, right? But this is congruent to 1 mod 7. Right? So you see, we know n is an integer, so that's good enough because as long as n is an integer, this thing is congruent to 1. So this is just congruent to 1 mod 7. Yeah, sorry. I accidentally thought that this was -1. So make sure you understand why it's 1. So, okay. Um, this question, this question is not as heavily modular arithmetic oriented. I think a lot of my next few are not. Um, Yeah, so we're just going to skip a little bit to this question because I think this question is more pertaining to the subject than the other. So again, try if you get stuck, try and see if you can generate a -1, a 0, or a 1 somewhere within this, uh, somewhere in your modular congruences. Yes, that's correct. Good job. So the first thing that you can see here is that this number is like very big, right? Very, very big. They're six to the 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 six. It is like absurdly big. You're not going to get an answer out of a calculator if you try and plug this in, right? I almost fell out of my chair. It's too big, right? So what we want to do instead is we want to sort of analyze this mod 7 because whenever we're asked for a remainder and it's a number theory question, it's like almost a given that we're going to use mods. So it's 6 to the 6 to the 6. 1, 2, 3, 4. Okay. So like this mod 7, right? So the first thing is we can do something very similar to our other one, in which we can make our 6 into a -1, right? Because 6 is congruent to -1 mod 7, right? So we can substitute -1 here to the 6, 6, 6, 6, da, 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 right? Mod 7 is congruent, right? I'm like, okay. We know that this is definitely going to be even because it's 6 to the something and 6 is even. So -1 to any even integer is going to give us 1. So we know this is 1 mod 7, right? So see how if you train your mind to be able to see these very quickly, then you will be able to sort of solve these questions very quickly, right? Um, The other strategy, if you didn't see that you could substitute in for -1 right away, is you could try substituting like different powers of 6, like 6, and then you get like 36. And you're like, wow, 36 is congruent to 1 mod 7, right? So every even if this is even, which it is, then we're just gonna have 1 times 1 times 1 times 1 times 1, whatever, right? And then since it is even, then we're just gonna have 1 to the power of whatever, which gives us 1, right? So those are two different ways you can do it. So first, always try and see if you can like make this into -1 or something. If that fails, just keep on going up the powers until you get to -1, 0, or 1 somewhere like that with these types of questions. So with the time that we have left, um, I could go over CRT, but I think that's a little bit too complicated for 3 minutes. So I'm just going to explain why our divisibility trick for 3 works, or like the remainder trick for 3, right? For 3, right? So for 3, um, essentially, let's say we have this big number. So let's say it's like 6783, right? And we're like, okay, we want to calculate the remainder when this is divided by 3, mod 3, right? And how do we do this without actually dividing by 3? Well, what we can do is this, right? We know that this number is 6 times 10 cubed plus 7 times 10 squared plus 8 times 10 plus 3, right? This is just our like base 10 expansion of our number. So this is the same, right? And what do you guys see about how we can sort of simplify this down a little bit? Remember to consider what we said with like the huge exponents and stuff. Okay, so I'm just gonna tell you guys. So the key here is that 10 is congruent to 1 mod 3, right? So we can replace every single 10 in here with a 1, right? So this is just congruent to 6 times 1 to the 3, plus 7 times 1 squared, plus 8 times 1 plus 3, which is just congruent to 6 plus 7 plus 8 plus 3. Right. So this is why our divisibility trick, our remainder trick, this is why it works, right? Because 10 is congruent to 1 mod 3. And you can guess what's next, right? 10 is also congruent to 1 mod 9, which is why our remainder trick for 9 also works, right? Because we can just do the same thing, mod 9, and we can just add up all the digits, right? Uh Sadly, we don't have more time to go over all of them, but think about our divisibility trick for 11, and think about how 10 mod 11 plays into the alternating sum type of thing. Okay? If you're interested in this kind of stuff. Okay. But if that's not, then yeah, thanks everyone for coming to class today. Those of you who are learning about math even over your spring break. And I will see you guys next week. Okay? Bye, guys. Yeah, hopefully you guys learned a lot.